Okay, let's take a closer look into the block diagram of OB1203, the all-in-one biosensor. You can see the green area and the yellow area. The green area are all the components in the package, in the module, which means it also includes two LEDs, one red LED and one infrared LED. You can see that these LEDs can also be driven from an external LED driver, but that's not necessary because OB1203 has also an integrated LED driver. An LED driver that can drive an LED up to 250 milliamps, which is the highest drive current on the market today. The yellow area here is the actual ASIC area. And you can see there are three different main functional blocks. Let's start with the block at the bottom left. First of all, we already talked about it. There's an integrated LED driver. There's also a photodetector that is used for proximity sensing, but also for heart rate and blood oxygen sensing. There is an ambient light cancellation circuit that is used mostly to compensate for light sources that are around the sensor. For example, your light bulbs, your fluorescent LED light bulbs, all the noise and flicker from those light sources is canceled out by this one block. There's also a crosstalk and offset cancellation circuit. Optical sensors, specifically sensors with light sources as well as photodetectors in one module, they will always have crosstalk. Optical crosstalk, that is, when light from the light source goes directly into the photodetector without penetrating the human skin, for example, in this case. This circuit eliminates that crosstalk and eliminates the offset such crosstalk would create. So we can focus on the actual signal that is meaningful in this circuit. So the bottom left is the proximity and biosensor block. The top left circuit is the light sensor and the color sensor. There are 5 different and independent photodetector ADC combinations, which is unique in the industry. Usually such situations are muxed architectures, where a photodiode is muxed through to a single A to D converter. In our case, we have dedicated A to D converters, which makes it much faster and much cleaner. You see 5 photodetectors. Of course, we have red, green, and blue. We have a photodetector that has no color filter over it, which is basically measuring white light. And we have a photodetector which is metal covered. What that means is basically this photodetector does not receive any light from the ambient. And the only thing it really measures is the inherent noise of the system. So we're using that information to subtract it from all the other information, basically eliminating the system noise out of the measurement. And this big block here is the control state machine block with all the registers, I2C interface, FIFOs, and a couple of filters. There's also fuses. These are not fuses like you would find in your car or in your house. These are actually the fuses that we use to calibrate and adjust the modules when we do final testing. These are one-time programmable fuses, which means each part is tested, and then the calibration parameters are put into the fuses that are used by the state machine to make each part identical to the next part. The bottom has a couple of control circuits, for example, power on reset. There's a high precision oscillator. It's not high power, it's a high precision oscillator, and a low power oscillator. The low power oscillator is operating when the system is in standby or when there is no actual measurement being performed. As soon as there's a measurement signal sent to the module, the high precision oscillator sets in and starts a very precise oscillator in order to make the measurements as accurate as possible. That basically concludes the discussion about the block diagram. But in general, you only need 3 signals for the I2C communication interface, a power, and a ground signal. So with 5 signals, you can operate this device. There are no external components necessary to operate OB1203.